we just talked about electronegativity, size, and the resonance structure. Are there all the factors that influence acidity? No, there are a few more. And we're going to talk about those others, when we get to, talk about other topics. But those three are major. So let's talk about some examples so you get the hang of it. Let's talk about these two molecules. Which one is going to be more acidic? Well, as we talked about, we justified the acidity, we explained the acidity by talking about the stability of the conjugate bases. So conjugate base is this molecule losing a proton makes a nitrogen negatively charged. That's the conjugate base forms of this one. And that's a phosphorus having a hydrogen there. So that's the most acidic hydrogen here. So when the proton goes away, we're going to have a phosphorus having a negatively charged. Then we're going to talk about which anions is going to be more stable, nitrogens or the phosphorus negatively charged. Well, if you're going to use the electronegativity, I would say the nitrogen has a higher electronegativity than phosphorus. So should we say this is a more stable than the other one? I mean, that's probably what you may think. But what you need to think about is, the size also can become a major factor. And then phosphorus is in the third row. Nitrogen is the second row. So what that means is the both of them, nitrogen and phosphorus, they're in the fifth column. Phosphorus are bigger than the nitrogen. So this being more stable by being a bigger anion. It's using a third shell. It's going to have all 8 electrons in total. So that's the reason we think this is more stable. So because of that, that's more acidic. There's nothing I can say that you got to do this, you got to do that. There's no such a thing here. I mean, I'm going to tell you an example of what you think about. But what I can tell you that is, if you're going to compare the atoms on the same row, like oxygen, nitrogen, carbon, it's on the second row elements, then I would say electronegativity will be the dominant factor. If you're going to compare like this, elements on the different rows, then the size will be the, probably the most dominant factors here. So that's something I can break down. But the question that you might get is all mixture of those things. So there's no way I can simply say that you got to do this and you got to do that. It doesn't work like that. This is another example here. We're going to have a sulfur having a hydrogen, oxygen having a hydrogen there. That's the molecule that will give the proton. So to talk about the acidity, we'll talk about the conjugate basis of that, which means a T proton form. Proton goes away, the remaining molecule is going to be negatively charged. The sulfur anion, that's a conjugate base form, so this one. Oxygen losing a proton, then you're going to have an oxy anion there, that will be the conjugate base of the other one. So let's talk about which ones are more stable. I mean, you probably sense that it's kind of the same reasoning here, but I mean, you've got to know certain elements, where they are in the tables. You've got to keep hearing the same things so you get to remember these things, but we're going to provide a period table with a test. So you don't have to memorize them. It will become to you with an exam. So oxygen is a more electronegative than sulfur, at least I can say that. But sulfur is bigger than oxygen because they are right underneath. Sulfur is right underneath of oxygen in the period table. Sulfur uses 3 shells, and then oxygen uses just 2 shells. So sulfur is a bigger anion compared to the oxygen anion there. So by the same reasoning, sulfur anion is more stable because it's bigger, even though it is less electronegative than oxygen here. I mean, some of you may think that maybe the size may be the dominant factors. Not always, as we just talked about. If you're going to compare the atoms in the same row, like the sulfur between the phosphorus, then definitely sulfur is better than the phosphorus because of the setting higher reactivity. In the second row, oxygen, nitrogen, carbon, and fluorine. If you're comparing those 4, then electronegativity will be the main thing. So you got to use a different reasoning for different things. Then there are something that change the acidity, not as big as a changing electronegative atoms or by change of size, but there are a little bit smaller factors, but that also something that you got to consider when you talk about acidity and ranking the molecule by acidity. So that examples are here. So these are 3 examples there. The most acidic proton in this molecule is the hydrogen on the oxygen. Same thing for that one, hydrogen and oxygen is going to be the most acidic one. Same thing for this one. So conjugate bases of all 3 are the oxygen being negatively charged, all of them. So same size, same electronegativity, and you can see that all of them will make a resonance structure. So if there's no other factors there, then all 3 should have the same acidity, but they don't. They do have a different acidity. So how can we figure out one being more acidic than the other, even though same size of the atoms, same electronegativity, and the same state of the resonance structure, which is not all 3. That is something we call inductive effect. What else in the structure of the molecule can influence that? So this is where some other thing can help for here. Fluorine. Having fluorine nearby to the oxygen, which is negatively charged, can help the molecule being stabilized. The reason is the carbon-carbon bond, the bonds are basically sharing electrons density. And then it becomes like a wire. So oxygen having a higher electron density here, but fluorine being an electronegative atom, it can pull electron density from this oxygen through the bond. I'm talking about through the bond. So that's something called the inductive effect. Having an electronegative atom nearby will alleviate a little bit of the electron density on oxygen. And that's why we can consider this anion is going to be a little bit more stable, compared to the one that it doesn't have like this. I mean, this one doesn't have no halogen there. So this one, I believe, is a better stable compared to this one. But what about the other side? It has also 3 carbon there. There's something called electron withdrawing groups, like a halogen, which is electronegative atom, or something possibly charged there that would be something considered is electron withdrawing groups. That can increase electron acidity by sharing some of the electron density through the bond. But if you have a carbon chain, the carbon chain is something we consider electron donating. It gives electron density through the bond. And then this one has a 3 methyl groups there, so 3 carbon here. That is basically what the other doesn't have. This one has just 1 carbon substituents. I mean, that may have 2 carbon substituents, but this one has 3. Each carbon donates electron density through the bond to the oxygen, which already have a 100% electrons increase. I mean, the 1 electron increase. So that carbon chain makes it worse for the oxyanion because the neighbors just keep giving electrons. I mean, it's a small fractions, but it increases electron density on oxygen, which is done by the neighbors. So if you compare between these 2, this gets a less electron density compared to that one because it has a more carbon chains near the oxygen anion. So that is also called inductive effect. Electron density being changed by the neighbors through the bond. So some works as electron withdrawing groups, that helps. Some works as electron donating groups, that actually makes it worse. So that changes acidity. So which one being more acidic among these 3? Definitely the one with electron withdrawing group, because that will lower the electron density of the oxygen a little bit, but it makes a difference. And then, of course, the one that doesn't have none of those things, but the one with a more carbon chain, that's the one that being punished by having too many electron donating. So this is a subtle change or fine tuning of the acidity by the substituents in the molecule. So these are something called the inductive effect, something that you got to think about. All right, so after that, let me tell you, I already keep the ranking here, but that's kind of this is just a hydrogen on carbon. I know this is a very less acidic hydrogen, but at least we can consider conjugate base forms of that. Conjugate base forms of this one, this hydrogen being pulled out, is what this carbon being negatively charged, and same thing there. All three conjugate bases having a carbon being negatively charged, it's the same element, so size doesn't matter, right? But what are differences? This one, you cannot draw any resonance structures. Compared to this one, you can draw the resonance structure by having this negative charge comes in, make a double bond here. That double bond has to come out. That means this carbon being having an excessive electrons, so that's going to be negatively charged. What it means is that you can draw the resonance structures. Same thing with this one. You can draw the resonance structure by this one comes in, make a double bond, that one comes out, make an oxygen negatively charged. So first of all, having a resonance structure means spreading the charge in the molecule that helps for the acidity or stability of the anion. So those two are better than that one. That is definitely the worst one. But among these two, how can we figure out which one is better? If you look at these resonance structures, carbon being negatively charged, carbon being negatively charged, there are no differences. But if you look at the resonance structure form of those, this one, after it makes the resonance structures, still the carbon being negatively charged, but there's an oxygen here. This resonance structures, now the oxygen is being negatively charged, which is a more electronegative atom compared to the carbon. So among these two, which ones are more stable? I mean, both of them make the one resonance structures, but this is definitely makes these resonance forms more stable, because if you think about that, these two will be the equal contributor, maybe 50-50. But if you look at these two resonance structures, I would say this is a major contributor, that's a minor contributor. The reason is oxygen can handle negative charges better than the carbon. So having a more stable major contributors in the resonance form, I would say this whole thing makes it more stable. That means this proton can go out easier. That means that this molecule is more acidic compared to the other one. So that is basically how the resonance structures can influence acidity. So there are several things you're going to do. Sometimes you have to use the size to explain the stability. Sometimes you're going to use activity. Sometimes you're going to use resonance structures. There are no particular order that you can use. It all depends on what you are comparing with.